Okay, we're going to go over electron flood theory, and I am going to show you, and I can prove to you that these things exist exactly as I'm saying they exist, and they interact with each other exactly as I am saying. I am not guessing. I have evidence to support my statements. CERN, Fermilab, they're really lost, literally lost, because they're working with gigantic particles, huge things, smashing millions and billions of particles together, and then digging through the debris and finding all these things. But they have no clue what it's about. I started with light, not gigantic things. I started with the smallest particles that exist and then broke them apart. Let's look at that first, and then we're going to look into how the atomic bomb proves my theory. Okay, as I said, Bohr is no more. And these are the particles that exist. The glowy electron, which creates electron showers, if you can separate the electron from the muon, you will get electron showers and you will get sterile muons, which means they stay exactly the same. The electrons will change from the white ball into a shower. And here it is right here. This is what CERN and Fermilab are asking for, muon neutrinos, which is the black ball. And they're looking for electron showers, which is the white ball turned into a shower. And here's what that white ball looked like before it showered. Here's the whole sequence of events. We took red laser, pulsed, put it into a highly tuned venturi that only allowed the white to get through, because the black is huge and heavy and hard, and the white is squishy, and I will show you that in a second. Now, what happened at the venturi is this is the particles I talked about, the black and the white. Again, there it is right there. You see that? That's the photon. There it is. All right. When it hit the venturi, the black and the white separated. Each half of that is an electron. That's an electron. Now, it consists of a muon and an electron neutrino, they would call it. But those two particles together make up what we always thought was an electron. A photon is just two of them together. And as they start to mass into a ball, a proton becomes stable at 1,839 electrons. There seems to be a mass of approximately 1,839 to 1,840 right in there that they shake and then they lock in at that, and then they become hard, really hard. And they can be broken apart. We know that because CERN does it. They smash them in bits and pieces, and there's no question you can break protons down into little bitty tiny pieces. So obviously it's not made of one big gigantic proton, and they just cannot get away from this. The standard model, they have to stick to that. Standard model does not even predict gravity. And they still have stuck to that. It's absolutely incredible. They say you can't accelerate light. Obviously you can accelerate light. There's no question. That's faster than the light that started. If light is light, and the light speed is light speed, that is the light speed, and that is faster than light speed. Case closed. I don't care how you cut it. There's no question whatsoever. And they're looking for the Higgs fields. We got them coming out of our ears because every one of these white particles turns into a field of Higgs, because when it concusses with the standard air that's here, which has the black particles, it starts to spin like crazy, and that's when you get these Higgs fields. But between here and there, it's pure white electron energy. It's only this part right here. All right? When we see this here, all we are looking at is the white electron. The black muon we saw went around. That right there is the initial blast of a nuclear bomb, and I will show you. Okay, it's Roger once again. Get ready to get nuclear. And what are we talking about today? Well, this is Professor Simon Holland. Very nice guy. And he's presenting some evidence that Lawrence Livermore Lab is trying to understand why they're seeing all this little anomalies out here way ahead of the shock wave. They can't figure it out. Now listen to what he has to say.
Refractive index difference goes over the smoke trails. Well, it actually goes between the smoke trails and you, the camera, and you see this, woo.
You see up here, watch, you see that, you see that, you see that, you see that, you see, all the way around, it's a circle, all the way around the shock wave. And they call this the shock wave. Well, this is the material that causes the shock wave. The shock wave is a magnetic shock wave. Now let's look again. Think about this carefully. What they did is they shoot up these rockets that are smoke trails, and then they see what happens in the atmosphere that disrupts these. And then they did see this anomaly, and they just can't figure it out.
In the smoke trails, and you, the camera, and you see this, woo.
See it?
This wiggle go up the lines. So the mystery for you today is, what causes it? What exactly causes the mysterious wiggle? If you know, tell Lawrence Livermore, because the truth is out there.
Yes, it is, Professor. All right, so Professor Simon says go up and tell Lawrence Livermore how this is happening, and here's how it happens. Now, when a nuclear bomb goes off, this is a sequence of events. They take an extremely dense, heavy ball of matter, and then they crush it so that all the particles crush into each other's fields. When they do that, so they crush this extremely reactive ball, so much tighter that it reacts and just goes insane, because the fields are reacting to each other's fields. And the only fields that react are the white particles. Don't forget, I showed you before many times, that's what the electron looks like. It has a dark and a white side. And the white side's the only thing that does anything, it explodes. It can explode and bomb and just huge spot or everything. This thing never changes. It stays the same weight and the same heavy. This can get small and get large. And this is the explosive part. Now, so here's what happens. And that they don't want to be next to each other, those white ones. They want to be away. So they congregate on the outside of all matter. That's why you can't see inside the matter, because that's where the dark matter is. The dark matter gets pushed to the inside. So electrons are crushed in this, and then they expand away from each other because they hate each other, and they go so fast that they pull themselves apart from the black core, and all that's left is a black core. And we saw that in the experiments. It exploded, and then the core turned black, and then it re-exploded again, because the black core wants those electrons desperately. They come back and they slam back into it, and then there's so many in there again, they go. But this time they're going with that dark matter with them. Before it was just the electrons, and all they do is burn. They're just extremely burny little parts, but they don't seem to have any mass. All the mass appears to be held, well, not all of it, but most of it appears to be held in the dark matter part, which is what they would call a muon, neutrino, muon. But so, and I say, the electrons have very little mass, but they burn buildings instantly. However, they don't push them down. They don't push them down, they just burn them. Next comes and that's just the white part, just the white part. Then comes the black and white part, which are the complete particles. And they hit the building and just tear it to shreds. And that's because of the dark matter. Dark matter seems to have an extremely heavy-duty reaction. So here, let's just look at this real quick. Can you see this? All right. This is what an electron complex is. It's not just an electron, it has dark matter. So the electron explodes into showers. The muon, which is gravity, muon, dark matter, it never changes. It's heavy and it never changes. The white part can go tiny, it can go big, it can squish, it can go like a ribbon or a fiber. It's manipulative, it's ductile, you can crush it. The black ones, they just don't do anything. They just stay, and they don't react to the magnetic fields or anything. That's why when the thing explodes, the black ones just stay there. They don't care about field effects, really. All they care about is bringing the white ones back. So this is a cross section of a proton. So you got An electron is just one of these little particles. A photon is back-to-back particles, and those bounce off. These burn into you because there's just one they want to incorporate. These bounce because they're basically neutral. This, at a proton, 1839, all of your dark matter is more or less pushed towards the center, and the coating on the outside is where your really explosive matter is. That's why when this goes off, all the white electrons leave, and they go so fast, instead of coming back where they're supposed to be, they're gone. So now you've got a dark core, and then everything comes back to it, and they come back like this, and then they go out like a shower. All right, and I'll show, let's just look at, but here's what I was really shocked at. I'm going to go to Livermore and say, hey, guess what I got? Look at this. And now, look at this. This federal funded research development center, Livermore, primarily funded by the U.S. Department of Energy. I tried to contact them many, many times, and they never have responded. They refuse to respond. Everybody, I've tried every one of these. I've tried Fermilab. I've tried all of them. And Fermilab, Don Lincoln just told me, we're not going to look at you because you're not peer reviewed. So there we sit. Now look at this. And now Fermilab is a whole nother set, just as bad as this. Look at this. This is Lawrence Livermore, government funded. These are all the people. I said, who am I going to send this to? There's a million, zillion people here. And they're all government employees. Government. Now, I guess the government's paying these people. Look at this. Look at this. This is just Lawrence Livermore. And this is just one of the government-funded agencies. And as far as I know, I haven't seen any of them produce anything that's of any significant value. I'm showing them how to split these photons into muons and electron neutrino showers, and they're just not, nobody will respond. Just so you don't fully understand it. This is the red laser. That's red laser accelerating. They say that's not supposed to happen. Well, it damn sure is happening. And when it hits here, because it's a tuned Venturi, the particle itself, which is being ripped out of the wave and seen right here, divides and does precisely, and I mean exactly, what CERN wants to see and Fermilab. The black part is the muon neutrino, is fissioned away from the white part, and then it's fused back here. That's fusion. So fission and fusion. In the middle is raw electrons, and this is what is the original impact of these houses, and they just burn. They don't collapse, they just burn. And then the next wave comes through, and it has both the black and white attached, and that takes it down. So it's the black particle that has the weight. Okay, again, a test house. And they put in, transformers and, gas tanks and everything. They want to see what is going to be the impact of this radiation on this type of a house and with all these different things that they have. And so now they're going to set the bomb off. Watch what happens. This is going to light up like unbelievable. Watch this. Boom. All right, nothing but brightness. 100% electrons at this point, and that's only these. It's not knocking this building over. If it was both of these, this thing would have been gone. It's only the electrons at this point. Now watch. Watch what happens to this house. Look at it burn, 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 burn. Look, it's just combusting, but it's not burning. It didn't blow it down. You would expect this to be blown down. That's because it was only electrons. Only electrons. And this gives me enormous hope for my device to harvest these electrons, because if we know there's a tremendous amount of energy here just to combust this instantaneously, a huge, huge amount of electrical energy, but it didn't knock the building down. If we could just get this, harvest this electrical energy, which we can using Roget's free energy device. Now, the laser, which would be putting out this beam of white particles, which I show, would be here. They're red because I can't make white on white. Got it? Now, it squirts them out here like unbelievable. Now we have to collect them before they combine back with the black ones. And at that point, we have this kind of energy. And it's not going to knock you over. It's not going to do anything. And we're only working with light. So we're not having any danger of being injured. Now, this is, again, only the white particles are coming first. So the white come out, and then behind them comes two of them at a time, which is because it's slowing down a little bit, and they're coming together at this time, and that'll be the next impact. And it just goes all to hell. Now, so what happens? At that point, everything goes this way. Now, the core says, hey, I don't have any electrons left. All you guys come back. And they come back. So this is the burning phase, only that. The next phase will be this, the concussive phase. Watch. Here they come. Boom. Come on. Boom. Boom. There it is. Now we're hitting it with the heavy-duty particles. And at that point, the core is just totally empty. It says, I have no electrons. You guys come back to me. Watch. It all goes that way. And now watch what happens. It turns around and comes back. You see it coming back at us? Well, okay, if you want to get into physics, you better understand nuclear missiles and nuclear fission and fusion and particles and all the different decay and nuclear interactions. Now, get your book. Make sure you got a book. Make a page called The Nuclear Bombs, and now start writing in information that we're going to get here, because this is from hold on, it is from Riddle. All right, and it's called How Atomic and Hydrogen Bombs Work in 10 Minutes. Now, I have not seen this yet, so we're going to find out ourselves, and this is how you do it. Don't just watch them and hope for the best. If you see something that makes sense to you, write it down in here about nuclear weapons. If you're interested. If you're not, well, just go about your life. But if you want to present information and support, then you better do it the way I'm talking about. Otherwise, you have nothing. All you do, oh, I saw somewhere the guy said this and that. Well, at least if you have something to write, and then you say, well, let's refer to this. Now, I'm going to try to take in only valid information. I don't know what they're going to say, but I got a feeling they're not going to have it right, because I think I understand nuclear theory much better than virtually anybody else. I don't care what they say. Laugh at me, call me a bragger, you know. But it's, if you don't understand electron flood theory, there's no way you can understand how a nuclear bomb works. Just no way. So let's see what they have to say, because I haven't seen it yet. Maybe I'm wrong. Let's find out, because they're going to go both the hydrogen and the atomic bomb. So here we go, because they're two different things.
Missiles that carry destruction. Ammunition that is incredibly dangerous, but still used. If nuclear weapons come to mind, then you have the right idea. Damage from exposure to hydrogen and atomic bombs is measured in millions of dollars, but no one really goes into details about why this happens. It seems to me that this is a very interesting topic for analysis. Therefore, today I'll tell you what's the secret of the destructiveness of these bombs, and indeed, how they work.
Okay, this is the kind of thing I love, because now we have a topic of discussion. I don't know what he's going to say. I have no clue. I have my already opinions backed up by my research. Now, let's see what their theories are and what their research supports.
Some people think that atomic bombs and hydrogen bombs are virtually the same. To some extent, this is true because both types of bombs are categorized as nuclear weapons. But to talk about the differences, first we need to understand the basic concept. Nuclear arms are weapons of mass destruction that use nuclear energy to create an explosion. This energy, in turn, is contained in atomic nuclei and is released during nuclear reactions and radioactive decay. I'm sure that the last two concepts are already familiar to you. I've mentioned similar processes occurring in the nuclei of stars several times before. But today, we move away from the topic of space and discuss what's created by human hands. So, if both types of bombs use nuclear energy, what could be the difference?
All right, let's discuss it. All right, so we're talking about an atomic bomb now, and these are all the different elements. And some of them are extremely heavy, and they will create atomic blasts. Now listen.
Usually, uranium-235 is used in nuclear weapons. You might have heard somewhere that not only uranium-235 is radioactive, there's also uranium-238 as well as uranium-234. Different numbers tagged to the end of an element are isotopes. To put it,
An isotope means that, in every theory, basically, the core and the atom has a certain number of particles that make it extremely stable. And then, and not when you get up in these ranges, they're never really very stable. But normally, your average types of elements are very stable when they are in the stable configuration. But if they have too many electrons or not enough electrons, that's when they become isotopes. And then they either are positively charged or negatively charged. They want electrons, they want to give up electrons. And when I say electrons, I'm talking about the two particles together, because they always travel together. They always travel together. There's going to be, the hanger-oner is the black one, the muon. It's always going to have a white one going with it. Now, I don't know, it might have more than one white one. I don't know. But when I see it in light, I see a white and a black and a white and a black, back to back, like two dipole bar magnets. And I think I've shown you, or I will, I'm sure you're going to see it, or you should have seen it hundreds of times if you've been following me. Here goes. So they're talking about looking for heavy elements and isotopes, which means that they're already unstable.
it's simply different types of one element. But we won't go into unnecessary details, because only uranium-235 can do what we're all here for: to obtain the maximum amount of energy during the explosion of an atomic bomb. The content of 235 isotope in uranium should be at least 80%. Therefore, in the production of nuclear weapons, uranium is enriched further. But if something goes wrong with this process, there is a fallback. You can also create a plutonium bomb, which will be based on the isotope with the number 239. However, this element is rarely found in nature, which means that you'd have to try and create it artificially. Now we know enough about the inside of an atomic bomb. But how do we launch such a weapon? The nuclear explosion occurs because a certain mass of fissile material is concentrated in one place.
Let me just explain. I'm sure he'll do a fine job of explaining it. However, I will make my own explanation. What they're going to do is force particles together, just almost like CERN does. He's just causing these huge, gigantic explosions because the fields are forcing the other fields, and they can't stay together. Just like the Venturi, only they have it encapsulated. This is going to come down and create a sphere like that. Now, if I made a nuclear bomb myself, I'd put all kinds of explosive devices around here, like with titanium plates, and put the fissile material in the middle, and when I let off the explosion on the outside, it would do that. But they're doing basically the same thing. They're shooting this down as like a solenoid. Toom. That's my take. I could be even wrong. Like I say, I haven't seen this, but I know what they're going to do is force the fissionable material together, and then all the fields crush, all the electrons go out, then all the other particles go out, and then they get sucked back because you end up with a black hole. And I've shown this, and again, you'll see it again, I'm sure, in a minute.
This can also be called critical mass. When it is reached, a nuclear decay reaction is formed with the release of energy. But
okay, this is not correct what he's showing. When these particles come together, yes, let's take this. What they're taking is, they're taking huge particles. There's no, the pluses are attached to the minuses in the core, in every single atom. Now, they're talking about these protons, and these are, I don't know what they're talking about, neutrons probably, because they don't even take into account electrons. They really don't even take into account, like they're not even there. So they think this is somehow going to be so crushed that it's going to break into two chunks like this. And it does. It does. I don't disagree with that. And these are so deadly because they're like machine gun bullets. I'm working with light. Light is nowhere near this. As a matter of fact, just one of these particles is 1839 or 940 or something like that times more than a light particle. Just one of these. And they're kicking out tons of them. Now listen, so it's an unstable nucleus. It breaks apart and they get a lot of energy.
For a powerful explosion, one critical mass is not enough. To get a truly destructive bomb, you'll need 4 to 5 critical masses of matter. There are several ways to achieve this, but I'll talk about the main one. It's called implosive. Imagine a nuclear bomb, for example, in the form of a small ball.
That's what I would do. I'm surprised. Okay, good. They're on the right track.
Inside it are all the necessary components for a nuclear reaction, but the critical mass hasn't been reached. In order to achieve this, we'll create a guided explosion from the outside. Suppose I put an explosive on the outside of the bomb and detonate it. When properly exposed, the space inside the bomb will begin to shrink towards the center of the shockwave. The density of uranium or plutonium inside will increase, and we get a nucleus.
Perfect, exactly. So what happens when you see all that white come out of there? All that came out of there was the white. The black is still in there. What you end up with, literally, if you could get inside, you would see this. That's what's inside there now. It's exactly like this. I have that ball of electrons. When it exploded, and that's all we can see is these glowy electrons coming at us. But what is left inside is this, is the black ball. That's the dark matter. So it's all by itself now. They cannot exist without the white. And it is so attractive that the pullback is just enormous. But originally, all we had was electrons. All these are electrons. And then, as all of the electrons left, then you started to get particles that were more than one electron. Chunks of particles. And primarily, you know, almost like dust particles, but they're bigger than light. The first part was just the electrons. And then the second part was the photons, basically, that had the dark matter. And, you know, because you can push things with light. Photons will push things. Do you ever see one of those, I forget what they call it, the radio jobber that spins in a circle when you shine the light on, and there's a black side and a shiny side? And they think that, and you have to hit it on the black side, I believe, to push it. They think something's wrong there, or I don't know what they think, but I can tell you what is happening, is the black is absorbing a particle and getting heavier and pushing. That's what happens with that. But this is what's going to happen. In the center, you have your dark matter. So now, all of these have gone. And the dark matter says, hey, where'd you guys go? Come on back. And then they come back. And that's what gives the pullback effect.
Nuclear explosion. What about the hydrogen bomb? In this explosive device, energy is released due to thermonuclear fusion. A very fast explosive reaction takes place inside the charge with the help of elements such as deuterium and tritium. Other heavier elements can also be used along with them.
Those are not heavy elements. Those are your hydrogens. Now, what is it with hydrogen? Why is that hydrogen so explosive? You ever see hydrogen go off? We used to take balloons full of hydrogen and then explode them with firecrackers, you know, these wicks and so forth. And boom, you run like hell to get out of there, because boy, when it goes off. And the reason it's so powerful, hydrogen, is it just becomes nothing but electrons. Everything else breaks into other bits and pieces of particles. But hydrogen itself is the one exception. Hydrogen is just nothing but particles. All right, hydrogen 1 and hydrogen 2 just means that your core is literally twice the size, but it's still hydrogen. It hasn't quite gotten up to the size of helium and that complexity, lithium and so forth. So, but it's a gas, and the gas, these particles can separate instantaneously, and they do, and they just become electrons. That's why it's so completely explosive, hydrogen, and it burns very hot.
Heavier elements can also be used along with them.
Okay,
However,
now why do they put the heavier elements in? The heavier elements are to cause the destruction. The hydrogen gives off so much propulsion, but it's just small particles. The heavier elements, when they go, they're throwing out chunks and bombs at the same time. But the hydrogen is what gives it the propulsion.
the main effective substance is lithium hydride. By itself, it doesn't produce an explosion, so clearly we need something else. The detonation of this substance is usually carried out by an integrated nuclear device with low power. In a simple way, it can be called a detonator. When it's activated, energy is released, which triggers an explosive thermonuclear reaction inside the bomb. Interestingly, for hydrogen bombs, there's theoretical.
It's a great day to help people customize and save with Liberty Mutual.
This guy's funny. We'll give them their ads, why not?
Theoretically no limit to the power. If you wish, you could create such a powerful bomb that it would simply wipe all life from the face of the earth. But I hope it never crosses anyone's mind. By the way, more about power. In the case of nuclear weapons, they're measured in TNT equivalent. Why is that so? TNT is an explosive and quite well known. To understand the power of a nuclear explosion, a certain amount of TNT is needed to produce the same energy. Usually it's expressed in kilotons and megatons, and I have some examples of various bombs. To begin with, the famous Tsar Bomba. It's related to thermonuclear, that is, a hydrogen type of weapon. Its power is 58.6 megatons. Simply put, it was such an amount of TNT that would have had to have been detonated in order to compare with this one bomb. As for nuclear weapons, the most famous are Little Boy and Fat Man. The first was dropped on the city of Hiroshima in 1945 and had a capacity of 13 to 18 kilotons of TNT. The second bomb destroyed the city of Nagasaki 3 days after the first. It had a capacity of 21 kilotons. The consequences of strikes with such power are not difficult to predict. First of all, there's chaos and destruction caused by a shockwave and light radiation. But there's also something that cannot be seen with the eyes. It's impossible to feel or hear. I'm talking about radiation. Radiation, one of the factors caused as a result of the explosion of nuclear weapons.
All right, I'm going to explain to you my take on radiation. I don't know what he's going to say radiation is, but I can tell you what I think radiation is, and my research shows it. When you take atoms like this, there are exact numbers of electrons that make up these atoms. Now, if you take nickel and you break it where it's in an extremely unstable state, it wants to be either down here to be cobalt or up here to be copper, if it's going to break down or change its state. So that's called nuclear decay, nuclear radiation. If it gives them up, it's shooting off particles. And when it shoots off particles, they're big. They're not just one little light particle like you're getting hit all the time with light. Light is a particle. Light is one of these particles. Absolutely, no question whatsoever. However, the particles they're shooting off at you are like this big. They're not one. And what happens is those kill your cells. And they're nuclear. Well, here's the thing here, right? This is a nuclear radiometer, a detector, the Geiger counter. And it tells you how much background radiation is going on, how many, and you're going to have clicks like, I'll turn this on right now, and it'll sit here for a second and it'll start clicking away at how many, and I think it runs 13, 14, 15 clicks around here. And it depends on where you are in the world, first of all, because it's background radiation, they call it. You've ever heard that? I'm sure you've heard that, background radiation. What is that? That means in the background, there's always going click, 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 click. And all that is there's a molecule that's becoming stable, or it's decaying. It's thrown off one of these little tiny particles. Now, after a while, it'll build up to what it's sensing, and then it'll start to create a graph of what's in here. And I look at it, I test different rocks and so forth, but primarily I don't find any problems with it. And this is the range that really is not going to hurt you. All right, this is just incredible. I can't even hardly believe it. This is the background radiation here in my shop. It's about 0.1 microsieverts. Micro. Now, they're talking about radiation from CAT scans. This is millisieverts. It's 1,000 times more than this. So if we had one, which we only have 1/10 of one, but if we had one here, this would be 10,000 times more than what's in my shop right now. 10,000. All right, because just one would be 1 microsievert. These are 1,000 for every one, and we have 10 of them for your belly. That's 10,000 you're getting instead of 0.1. 10,000 of them. That's insanity. These are CAT scans. That's the background radiation for 3 years. And some other ones are even more than that. No, I guess not. 4 years, coronary. Now, people are getting CAT scans like it was just common sense. Now, look at this. This is for cancer. For cancer, you're still only getting 10 to 20 per procedure. And they can add up over time to be more than 100. But you're already getting so much just from a CAT scan. It's unbelievable. It's as much as you're getting from radiation treatment for cancer. Something's not right here. This is interesting. This is radiation exposure imaging testing. Is there an increased cancer risk? This is National Institute of Health. Yes, there is. Not only is the radiation dose per procedure and the cumulative radiation exposure concerned, the rate of exposure must be considered. You're getting 60,000 times more radiation in an hour than you would get for years. And they're talking about the debate over, I'm telling you what, you better just start doing your own research, because every time I look into something, I get really, really upset, because I'm finding out that there's very little concern for the reality of the situations. It's the reality of the people in charge of making the decisions that it matters above the reality of the truth of the situation. And this seems to be in everywhere, every single place now. Very upsetting. I couldn't believe this. My wife just had CAT scans and PET scans and all kinds of things. And, I just didn't even think about it. All right, there's their recommendation. Best and safest recommendation is time for patients and physicians to minimize exposure to all forms of radiation and to discourage unnecessary testing. And then there's the competing interests and so forth. So you never know. I mean, they always end up saying the right thing. Well, look, watch this. Wait to hear this. You see this? This is a tragedy. This is from the National Institute of Health on probiotics and the prevention and treatment of COVID-19. And if you go through the whole thing, and it's very detailed, and it says saving lives, flattening the curve, the most important things we can do. And then they go on to say that probiotics is the way to do it. And let's get down to the conclusion down here. Evidence supports probiotics' role in regulating the immune system, suggesting a definitive, that means absolute, role for probiotics in viral infections. You could come up here and read the whole thing, but just let me home in on it so you can stop here and read it if you'd like. The bottom line is, it says that, well, currently there's no random controlled trials, so they don't know what's going on, but they know that supplementation of probiotics, high risk and severely ill patients, frontline, might limit the infection and flatten the curve. I haven't heard one word from anybody about probiotics in the healthcare systems, not a word. And I've talked to a lot of doctors, asked them about it. Do you recommend anything with probiotics? No, we don't care about that. But probiotic supplementation could reduce severity, morbidity, and mortality. Probiotics can inhibit cytokine storms by simultaneously boosting your own immune system and evading the trying to fight against it, because it fights for you. To adapt is the challenging. It's to respond quickly to the viral onslaught. The probiotics-induced suppression of the inflammatory cytokines response may prevent both the severity and occurrence of acute respiratory distress syndrome, which everybody's dying from, making probiotics an attractive adjunct, which means add-on. And this is not a single word about this. And this is from not too long ago. This is from just 2021. But they go back 10 years. And they have the almost identical same article 10 years ago about probiotics preventing disease and boosting your immune system. And that's why we have so many people that are immunocompromised. They've been taking antibiotics and their immune systems are damaged. Their guts are damaged. They have diarrhea. They have bloating. They have cramps. They have all kinds of problems with their digestive system. You don't digest right, it means you don't have the probiotics. You don't have the probiotics, you're going to be sick, you're going to be invadable. And this is what not a word, because even the people that are getting the vaccines and everything, that's going to help them. I have nothing against the vaccine whatsoever. However, they're going to come back and get sick again because they're still invadable. They still have immunocompromised systems because they don't have the probacteria to do the right jobs. And this is what we need to look into, is that. And see how things cascade. We went from atomic bombs to COVID-19.